In this problem, we're given a variable electric field, and we're asked to find the net charge that's inside of the cube. The length is, of course, 2 meters. So we have to basically be very thankful that they've already broken this up into components. Look at that. Usually we'd have to do this on ourselves, but we can kind of see that if we were looking at J, it's just going to go straight from one side to the other side and essentially just cancel out. So this we can get rid of. This K1 is going to go straight from, the bottom here to the top, and that's going to cancel out. And then this one, though, this one has an X. So we know that that's going to be changing at different things. So you can think of a bigger vector here, and then maybe a smaller one here, and then maybe if we go to the negative side, it'll actually start pointing the other direction. And this is really important because this is where I was getting this wrong, is I didn't realize that when this thing was on this side, it was pointing in this direction. When it was on that side, it's pointing that direction. And the question is why? Because when we plug in our x values, here x is actually equal to 0 on this side. And on this side, x is equal to -2 meters. So, because the length is 2. So, when we plug that in on the front side, e to the front is going to be equal to 3.34. because that's going to be 0, so it's just 3.34 in the I direction, right? And so you could see it's going to be going positive in this way. And that's actually the same direction as a normal. The normal is this one. So because the normal and the electric field are going to be the same direction, we know that this side is also just going to have the electric flux being equal to E times A, which is going to be 3.74 times 4. Because over here the length is 2, and so the area is going to be 4 meters squared. So we'll just plug that in over here. Newtons over coulombs times 4 meters squared. So on this side, we'll get, we'll keep in mind, I want to stop at this point because I want to note that this is a positive EF on this side. I'm not going to calculate anything besides just the EF at this point. I want to calculate the EF first. And then I'm going to go to the other side and I'm going to calculate the EF on there. So let's go to that side. The EF, E to the back is going to be now this -2 here. So we'll plug that in here. 3.73 times -2 plus 3.34. And that's going to be -2 times 3.73 plus 3.74. It's only just going to be negative 3.72. Well, this is the negative I direction, right? So you can kind of think of it that way. So negative E on this side, meaning it's pointing in that direction, not in this direction. So that's interesting. We actually have negative charges, negative electric field pointing in that direction. Now, it's really important to remember that when we plug this into our equation for EA cosine theta concept, these are magnitudes. So it doesn't matter if this is negative or positive. The cosine is going to take care of the negative or positive at the end. So get rid of the negatives and positives. The only thing that the negative is going to show you is the direction of the field. So once you know the direction of the field, get rid of the negatives and positives and take the magnitudes here. These are magnitudes. I just want to point that out before we go further here. These are magnitudes. So when I plug that in now, it's going to be 3.72 times 4. And then the cosine is going to be, notice it's 0 degrees here. So again, this is just going to cancel out. If that were 180 degrees, then this would be negative. But it's not. It's 0 degrees, and so that way it's positive. And these are magnitudes. Great. So now we can, and we'll just go like that as well. So when I add together the front side and the back side, because I'm just calculating everything together. We know everything else is just going to be 0, so we're just going to add these two together. We're going to get the total of 14.88 on this side. And then on this side, it is 3.74 times 4, which is going to be 14.96 on this side. We add those together, and we're going to get 29.84 in total. Then we can use our equation of the Gauss's law, which states that Q over epsilon naught is equal to the net flux. So 29.84, and then we can put this on the other side. And when we multiply that out together, 8.85 e to the negative 12, we get a total of 2.64 e to the negative 10 coulombs. And that's going to be the total charge. So, yeah, this is kind of a crazy problem.